Our next model is called the AlexNet. It's called the AlexNet. It is named after the author, the first author of this research paper. I'll provide you reference links to all these URLs. This is a simplified version of AlexNet, which is easier to understand. I'll also refer you to the actual research paper here. This is the actual research paper, and the first author is Alex. I don't know how to pronounce this second name, so I'll just say Alex K. There is Ilya and Jeff Hinton. Jeff Hinton, remember, this is the guy who actually created backpropagation in the late 80s, who actually reinvigorated, who actually gave a rebirth to whole of deep learning, right? So Alex, I think if I'm not wrong, is a PhD student under Ilya or Jeffrey or Jeff Hinton. And this is a very nice paper from 2012, and this is like one of the most seminal papers. This was the actual model. AlexNet was the model which in 2012 was applied on ImageNet dataset that we discussed in one of the previous videos. And this literally created the big wave of research and funding and developments in deep learning. Because AlexNet broke all the records of pre-existing non-deep learning based techniques, and it showed how powerful deep learning could be, especially for the given problem of object recognition, which is a very hard problem actually. So this paper is actually fairly easy for you to read, but I'll go through the most important things. Okay. Okay. Before we go into the paper itself, let's understand the architecture quickly, right? So you're given an input image, which is 224 pixels by 224 pixels by 3 channels. There is your red, green, blue channels, right? So this is your input image. The first operation that I'll perform is a convolution operator with a stride size of 4, right? With a stride size of 4, and I have kernels which are of size 11 cross 11, and I have 96 such kernels. Okay, so this results in, basically, if you apply your stride and convolution, everything, you will get 55 cross 55 sized images, and you'll get 96 of them because you have 96 kernels. So you get a 3D tensor here, which is 55 cross 55 cross 96. Sometimes this 96, the depth here, this is 96, this is 55, and this is 55. You can think of this as a 3D tensor which has a length of 55, a width of 55, and a depth of 96. Or in other words, you can think of this as having 96 channels. Just like the way this has 3 channels, you can think of this as having 96 channels. So first layer is convolution. The second layer is max pooling. So I'm performing a max pool with a pool size of 3 cross 3, with a max pool kernel of 3 cross 3, with a stride of 2. So this results in an image which is 27 cross 27 cross 96. This is again a 3D tensor with 96 channels here, and 27 length and 27 width. So what have we done? We have done one convolution followed by one max pool, right? The second step that we'll do is we'll again perform convolution, right, with padding. So this is the same. Whenever I say same here, whenever same is written here, it means in keras pooling equals to same, right? This ensures that things are taken care for, right? This ensures that this input size is 27 by 27 and this output size is also 27 by 27. That's what the same pooling equals to same will achieve. We have 5 cross 5 kernels and we have 256 such kernels. Okay, so we are getting a 3D tensor now, which is 27 by 27 with 256 channels or a depth of 256. Then again, we are performing max pooling here. Look at one thing that's happening. Initially, we used a kernel size or a filter size of 11 by 11. Then we are using a kernel size of 5 by 5. Then again, we perform max pooling again 3 by 3 and a stride length of 2. So this creates this type of matrix for us, which is 13 cross 13, which is 13 cross 13, and we are having 256 such, and this 256 just moves here, right? Because it's just a max pool layer. Again, I perform convolution, again convolution, again convolution. Look at this. I have 3 by 3 convolution with padding, 3 by 3 convolution with padding, 3 by 3 convolution with padding. That's why you have this 13 by 13 here, same 13 by 13, same 13 by 13 here. Okay, that's because you're using same pooling, right? You're changing the number of kernels or number of filters here. So eventually you reach 13 cross 13 cross 256. Then you apply max pool, right? With a stride length of 2 and a 3 cross 3 filter, max pool filter. So eventually you reach this 6 cross 6 cross 256. Okay, these cuboid shapes are very interesting because now look at this. You have length of 6, width of 6, and a depth of 256. Right? Then we apply the flatten operation. So if you multiply 6 by 6, which is 36, if you do 36 cross 256, what you'll get is 9216. So this is a flatten operation. Right? When I have a flatten operation, then I have fully connected layers. I have two fully connected layers followed by my final layer, which is a softmax layer. Because remember, what was this network trying to achieve? It's trying to solve the ImageNet problem, which is a 1000 class classification problem. Right? Now there are a couple of things that you should note. The kernel sizes here, 11 cross 11, 5 cross 5, right? Here you have 3 cross 3. You have all types of kernel sizes, right? And remember, this is one of the most successful models as of 2012. Lot of things have changed since then. We have a lot more discipline in building models. We'll see very far more complex models in some of the future videos in the same chapter, right? So people have designed. So Alex and his team has designed this network after lots and lots of experiments, right? So the key thing here so let's go back to the research paper since we have understood the architecture. There are a few important things that we should note here. The first one being the activations that were used in this research paper are ReLU. Remember, in 2012, ReLU was still a very new concept, very new concept, but ReLU worked very well, number one. The second very interesting aspect of this is they use dropouts, which was also a very young concept as of 2012, very new concept. Okay, so ReLU was a very successful concept. It's still used extensively today. Dropout was also a very successful concept, and it has stood the test of time. Right? Even 6 years today, as of 2018, even after 6 years, we still use ReLUs and dropouts. And this paper also used multiple GPUs to train, which is what we are doing today. Right? So these three very interesting stuff that the AlexNet paper introduced us. Actually, ReLU was not invented by the AlexNet paper authors, neither the dropout. They were discovered by different teams. If I'm not wrong, Dropout was discovered by the same team, which was headed by Jeff Hinton, by a different PhD student or a master. The Dropout was by Nitish Srivatsa, who was a master student under Jeff Hinton. So it's the same research group under Jeff Hinton, which created a lot of these very nice ideas. And GPUs, I think, were first used by Andrew Ng and his team at Stanford. So the very first set of GPUs that were used for deep learning were used by Andrew Ng and his team. So these are very nice ideas that were being designed at various universities. And AlexNet was one of the first big success stories to have used all these three concepts. But this is important. There is also one concept which is there in AlexNet. It's called local response normalization. It's called local response normalization. This is a concept. It's also called as LRN. It's a concept that was introduced as part of this research paper, but it didn't stand the test of time. People eventually said LRN really doesn't matter, and people started using stuff like batch norm, right? And let's understand what LRN does. So imagine if you have a 3D tensor here. So for every pixel here, you have a bunch of pixels lined behind it on the depth angle. So imagine this is a 26 cross 128. So if you take one pixel here, this one pixel has 128 values behind it, right? So if you take just the depth, if you take this and write it down as a vector, right? You get 128 such values because this has a depth of 128, right? So if you normalize this vector, if you normalize all the depth vectors, right, if you think of these as channels, right? If you normalize each of the channels, okay? So this is simple normalization, like normalizing a vector. So you perform simple normalization of a vector, but instead of normalizing the whole tensor, you're only normalizing each of these vectors. So you normalize this vector, and then you normalize this vector, which is here, you normalize this vector, and so on and so forth. That's called local response normalization. Today, we don't use that anymore. Actually, even if you don't have local response normalization, things work fairly well. And today we have better normalization schemes like batch normalization, right? So this paper introduces a bunch of very interesting ideas. This is the local response normalization part in the research paper. Don't worry too much about the mathematics. It's simple normalization on the channels. That's what it means, right? So training on multiple GPUs is an innovation in this research paper. They also use ReLU nonlinearity, which was extremely successful. They also use dropouts, if I recall. Okay, overall architecture. Okay, reducing overfitting. I think they have pooling as usual. We have seen pooling already exists. If I recall, they also had dropouts. Okay, the data set. Okay, let me go down. I think dropouts have been used in this research paper. Okay, so there is data augmentation. Remember, we talked about data augmentation of flipping the images, reflections, skewing the images, and things like that. They have also used it. Yes, they have used also dropouts. So this paper used some very, very interesting ideas like ReLU activation, like dropout, like using GPUs, like data augmentation, right? All these are phenomenal ideas that we still use 6 years later. The only thing that we don't use is the local response normalization. Except this, everything in this paper is literally gold. Okay, so this paper is a seminal paper, and I'll also point you to some code written by a student at, and I also provide the reference link for this. This is, I think, a lecture notes at Yale University in the statistics department where they taught this. Remember, please note that this is not the exact implementation of AlexNet. This is a slightly modified implementation of AlexNet. Instead of doing it for 1000 class classification, right? This is only a sample code that I'm showing you to show how easy is it to implement any model in Keras, right? So instead of the 1000 class ImageNet problem, this sample code is on the MNIST data. This is MNIST data, AlexNet, right? Just see how simple it is. This is your layer one. You have convolution followed by activation followed by max pooling. Convolution, activation, max pooling. Then you're doing some zero padding, convolution, activation. Zero padding, convolution, activation. Actually, you can move the zero padding here if you want, right? Some zero padding, convolution, activation, max pooling. Flatten, dense, 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 dropout. Very, very simple. Literally, this is as if by just look, this is literally like the code form of this diagram. Actually, in Keras, it's so easy that if you have this diagram on your notebook, you can convert it into code and run the code. You can convert it into code in like under 10 minutes. If you have all of these details here clearly, you can easily convert into code in literally 10 minutes. Okay, and at the end of it, you compile with whatever optimizer you want and then fit it. That's all there is. It's that simple. And this is a very, very simplified version for MNIST 10. Right? Very, very simple. So, but this paper has been seminal because except for LRN, every other concept that was used in this paper to solve the ImageNet problem are still very, very popular ideas.